I'm going to have to bring Margaret with to all my talks and have her do our introductions. So what I'm going to do is kind of a traditional talk for 45-ish minutes, and I'm going to do the history of computer architecture in 15, and then talk about some big challenges facing the field and then opportunities, and then I'll do questions and answers, and then I'll give you my life story, lessons learned, and then a Turing Award, and I've added a slide just for this talk, and because the content of that slide, when I gave a talk at a forum, a Turing Award winner, Ivan Sutherland, said, that's the most important thing you've said the whole time. So you're going to get that at the very end. All right. But first, we got the Turing Award, I guess, just a little over a year ago it was announced. And my friend John Osterhout at Stanford University said this amazing thing, because he used to be a faculty member there. There's now been 51 Turing Awards, or 52 Turing Awards now. 7 of them were done at Berkeley, which is a remarkable number. So it's kind of, you can say, where are the people now? Where did they go to school? Stuff like that. The research that led to the awards were done at Berkeley. So how many is 7? That's as many as Stanford and MIT put together. That's how many 7 is. So it's a lot. So to celebrate that, we held a series of lectures last fall, and they're all recorded, and including I interviewed the Turing Award winners, kind of a personal thing. So both the actual lectures, which are pretty cool, but the interviews are really interesting too. And I'd say themes of often people were doing something what got the Turing Award was something that was not seen as conventional wisdom, something that people thought was not a good thing to work on, and they give their stories of how they persevered. So I'd encourage you to take a look at that. Okay, 50 years of computer architecture. I think there's a couple of lessons, we'll see them incorporated, that software advances can inspire architecture innovation. Whenever we can raise the hardware-software interface, that can create opportunities for innovation. And the way we settle things in computer architecture was we come up with these ideas, we argue about them, and then companies spent billions of dollars to put in the marketplace and see who wins. It's not a perfect way to arbitrate, but that's kind of the way it works. Okay, just in case some of us have forgot our computer architecture, what is an instruction set architecture? When software talks to hardware, it has a vocabulary. And those words are called instructions, and the vocabulary is instruction set architecture. So a program is like a book. It's written in the words of that vocabulary, and it determines what software can run on that hardware. So programs are written in a particular instruction set architecture. Okay, with that quick review, let's go back almost 60 years to IBM. And IBM had 4 instruction sets at that one company. Each had its own I/O system, its own software stack, in different market niches. And so the engineers in the early 1960s had this idea at IBM that they would bet the company that they could have a single instruction set that would cover all these 4 independent lines. And they called that the IBM System360. Now the problem then and now in designing computers isn't kind of the brawn, isn't the data path, the arithmetic unit. It's the control, the brain. That's the hard part to design. So they needed a technique that could bring all these 4 kind of independent companies at IBM to be able to do the same instruction set. So they went to Maurice Wilkes, the second winner of the Turing Award, a computing pioneer, and he had this idea of how to simplify control. He said, let's specify control as a 2-dimensional matrix. And we'll call each row of the matrix a micro-instruction, and the 1s and 0s will control the control lines. Why did he think this was a good idea? It'd be easier to specify as a matrix. Also, in his technology, the logic was much more expensive than the memory. Read-only memory was so much cheaper and faster than RAM. And so now, programming, the control was like programming. That was his idea. So IBM, as part of betting the company, decided to bet on Maurice Wilkes' idea. And in April of 1964, they announced the biggest announcement in the history of the company. And they announced a family of computers that were all what we would call software compatible, binary compatible today. As you can see, the smallest one was 8 bits wide, and the biggest one was 64 bits wide. The memory speeds were different. And in today's dollars, the cheap one was $1.5 million, and the expensive one was almost $9 million. And so IBM bet the company on this idea, and they won the bet. They dominated the mainframe market for years. This was led by the 360 effort was led by Fred Brooks, who was another Turing Award winner. And to this day, those mainframe computers are still a $10 billion a year market. So 55 years later, that's still today what they did in the 60s, this remarkable achievement. All right, so let's move now. Instead of the way they were building them then, we started using transistors, semiconductor transistors. I mean, for that, so the logic and RAM and ROM are all the same thing. The speed's about the same. But Moore's law now applies because we're in semiconductors. And so the memory for that microcode could get bigger. And they basically have an instruction set interpreter inside it. So it allowed for a bigger instruction set interpreter, a more complicated instruction set. A classic example of that came from Digital Equipment Corporation, where the other ones were like 50 to 80 bits microcode and maybe 1,000 words. This had 5,000 words, each 96 bits. And that was typically what was done. Now the microprocessor people now coming to the West Coast, went from New York to Boston, now to the West Coast, they weren't all that good at computer architecture, so they kind of imitated what the other people did. And then people were writing for these microprocessors in assembly language. So they'd show off a new instruction by showing how an assembly language sequence that my computer is better than yours. So Gordon Moore of Moore's law of fame had this vision that the next thing they did after their 8-bit microprocessor, the 8080, was going to last for the lifetime of the company. So he decided, as a visionary, to hire a bunch of PhDs in computer science, keep them out of Northern California, send them to Portland to design the next great instruction set that was going to last for the lifetime of the company. This was called the 432 eventually. It was originally the 8800, better than the 8080. Incredibly ambitious, even to this day ambitious. It had ideas like a 32-bit address space with capabilities inside for security, an object-oriented architecture. It even had a custom operating system written in that time, the new programming language Ada. So really ambitious, because it's going to last the lifetime of the company. Alas, it had all kinds of performance problems and usability problems, and it was late. So they had to go back to Gordon Moore in 1977 and say, you had this idea of the next great instruction set, we're not going to be in time. So Gordon Moore was forced to launch an emergency project to provide a 16-bit computer in time for the marketplace. This was called the 8086. The people who were doing it were given 52 weeks to do everything. 52 weeks to design the thing, develop the software stack, and build the chip itself. So they spent 3 whole weeks on the instruction set. 3 whole weeks on the instruction set, maybe 10 person weeks altogether. And it was basically compatible at the assembly language with the prior level. And it was announced without much fanfare in 1978, but they were on time. Unknown to Intel, IBM was deciding that it was going to try to get into the personal computer market to compete with Apple. And they really liked Motorola's microprocessor, 68000. Its instruction set was very similar to the 360, and it was kind of elegant. But Motorola was late, so they decided to go with the 8088. Now, at the time, IBM had estimated that the sales over the next 5 years was going to be 250,000, which would be nice. They were wrong. They were off by a factor of 400. It was 100, or it was 4,000. It was 100 million. So suddenly, Intel's emergency project designed in 3 weeks became this incredibly valuable instruction set architecture because it was binary compatible with all the PC software that was booming in sales. Okay, this next comes kind of a research analysis of these microcoded machines which were popular. Now what happened while this was going on is the hardware-software interface was raised from assembly language to high-level language programming. High-level languages existed before then, but there were beliefs that in some circumstances you had to do it in assembly language, like writing an operating system. Well, the Unix guys came along and wrote a whole operating system in a high-level language, so that meant we could use high-level languages everywhere. So now what mattered wasn't so much what assembly language programmer could write, but mattered what was the output from the compilers that would translate the high-level languages. So John Cock, who was another Turing Award winner, His group at IBM did work in both architecture, but particularly in compilers, and they had advanced compiler technology. They thought they would do an interesting experiment. They'd take that famous IBM 360 instruction set, and instead of using all the instructions, they use the simple instructions, like loads and stores and register. And what happened was, once they did that subset instruction set, it ran up to 3 times faster, which was like a shocking. By leaving things out, they could produce faster code, not using the complicated instructions. So that was in New York, and then we go over to Boston, and some researchers at DEC who did the VAX analyzed the VAX, and they found, first of all, that the average number of clock cycles in this interpreter was 10. So 10 clock cycles per instruction, which was about twice as many as they expected. And then they examined the microcode, and 20% of the complicated instruction set was 60% of the microcode, and it was almost never used. So this called into question this idea of big, complicated microcode interpreters, and for these complicated instruction sets, what's the benefit of all that? So basically, now if we go back to our analogy, so what's a reduced instruction set computer? It's that vocabulary, the instruction set architecture, but it uses simple words. Now, basically, they're kind of as simple as microinstructions, just not as wide, which allowed us to use pipelining techniques so that you could execute them on average faster. And by the way, the CISC instructions that were left out weren't used out often everywhere, so how much did you lose? That RAM that contained the microcode interpreter now could be the instruction cache. So we could we could have a small buffer that would have the user visible instructions, which in the microprocessors we use all the time. So it's kind of like compiling versus interpreting. And that contents of that memory now would change to whatever program was running. And there was a breakthrough in what's called register allocation for the compilers called graph coloring that made it much more effective to use registers in compilers. So this is that transition. This is where Berkeley and Stanford come to the scene. At Berkeley, as an assistant professor, I led a project that was done in 4 Berkeley courses on the quarter system, where we investigated the ideas and eventually built a microprocessor that was called RISC-1. 2 of the students in that group decided to build a more efficient one called RISC-2, and at the same time, Hennessy led an effort at Stanford University called MIPS to build those things. And this was this remarkable moment in time in 1984 when these were presented at the leading circuits conference in San Francisco. And I remember, when the presentations were done, there was this murmur in the audience of, a couple thousand people. And it was a remarkable moment in time in that graduate students, a handful of graduate students at Berkeley or a handful of graduate students at Stanford could build a microprocessor that was arguably better than what industry could build. So we had to try and explain how RISC would work. They're simpler instructions. So basically, because they're simpler, you'd have to execute more of them. But what would happen is that we could execute them faster. So that's kind of the informal thing. So you can imagine if you were reading a book with complicated instructions that may take fewer, or complicated words that take fewer words, but it may take you longer to read them. But if it's simple words, you can read them faster. But that was kind of, that was the qualitative one. We actually was able to break that into a formula of the 3 pieces of the instructions per program, the average clock cycles, and length. And surprisingly, computer architecture at that time didn't have formulas like this. So John and I put that together in a textbook called The Quantitative Approach, which came out in 1989. And kind of the Turing Award is for kind of this slide, I'd say, is some part of it is our research contributions and the book that kind of explain a more quantitative approach to do computer architecture. Okay, so we're in this PC era where this is exploding and taking off. Intel, which is a great engineering company, put together a 500-person engineering team, which is remarkable, and had them build a better microprocessor. So what they decided to do is if RISC was a good idea, but they wanted to be compatible with the PC software, they would on the fly translate the x86 instructions into RISC instructions in hardware while the program was executing. And then any good idea the RISC guys could use, they could use, plus they were compatible with all its software. And they got up to 350 million per year. And so the x86 instruction set dominated not only the desktop, but servers as well. So basically the marketplace picked the PC, x86 in the PC era, The post-PC era, things changed. First of all, it's not buying microprocessors from a company. You're building a system on a chip, and you're getting intellectual property of pieces to integrate on your chip. So that's a change. Secondly, because it goes into cell phones and things like that, you care about cost, and so die area and energy as much as performance. So that extra overhead of translating instructions was expensive in area and in power. So that made a x86 unattractive. The volumes are amazing. More than 20 billion chips with processors, 32-bit and 64-bit processors in 2017, and 99% of those processors are RISC. So basically the market settled, and in the post-PC era, RISC won. Okay, so let's talk about some challenges going forward. Moore's law has been around, as long as before I was in computing, really, when I was in high school, I guess. And he said doubling the transistors every year, and then he amended it in 1975 to doubling every 2 years, but we're way off from that. So using Intel's technology, we're off a factor of 15 from where, if Moore's law still continued today, we'd have 15 times as many transistors. So we're way off from that. And so we're in the post-Moore's era. Another lesser known technology or observation is by Dennard. It's called Dennard Scaling, is how could we keep putting so many transistors on the chip and not burning up? It's because as we would double the number of transistors, we would shrink the feature sizes and lower the threshold voltage, and that would allow us to have basically the same number of transistors operating faster but using no power. Well, then in around 2007 or 8, that changed. So the blue line starts going up and to the right, is that we could no longer lower that threshold voltage, so the power started going way up. So we started running on a power budget, and that turned into kind of the end, and the practical implication of what people thought was Moore's law. This is the first figure of our textbook, and it started off with doubling before 1985, doubling every 3.5 years. In that RISC era, for almost 20 years, it doubled every 1.5 years. For those of people who weren't using computers in that time period, you would throw your perfectly good computer away because your friend's computer was newer and a lot faster, and you were jealous. And so you'd throw away working computers because it wasn't as fat. It was 2 years old, and your friend's computer is much newer. People don't and today what's happened? Well, the end of Dennard scaling, we tried multi-core, but there's limits to how many cores you can use. So last time we measured it, the performance went on only 3% per year. So that's doubling every 20 years. So I just threw my laptop away. Why? It broke. And I was not jealous of anybody else's laptop. It just wouldn't work anymore. So I had to buy another one. The flash drive stopped working. But so this idea of rapid improvement is over, although our software colleagues expect the hardware to make their programs continue to go double every 18 months. Their appetite for improvement exists, and at a time we're run out of being able to deliver on it using standard techniques. This is the point where if I was asking questions, people would say, what about quantum computing? So that happened so much, I decided I would quote a couple of slides to say quantum computing is not right around the corner. So the good news is companies are investing in it, and they've got some beautiful results. But keep in mind, we're not going to have a quantum cell phone, right? This is something in the data center, vibrations, cooling, and stuff like that. It's really high-tech science. And the number one recommendation of this workshop that CRA did, I guess a year ago, was they need a killer app, basically. For the next decade, given how limited number of qubits they're going to have, they need to find something that they can calculate that people would care about. Otherwise, people might lose enthusiasm for it. So that was a CRA workshop. That wasn't sufficient, discouraging for some people. So I got another one, and this was done by the National Academies, released just last December. And basically, and it's got, where it's the EE chair, Stanford chaired it, and people in quantum computing from all over great places, well-established people, and the quote was basically the same thing. So quantum computing is like a 2030 kind of thing, hopefully. Hopefully in 2030 it may be useful. Maybe it'll take longer than that. So we need something for the next decade. There's nothing coming down the pipe that will be commercially significant for the next decade. Another, so, more bad news is the security challenge. Is computer architecture was defined that it's correct as long as you get the right answer. It doesn't matter how long it takes to work. Timing doesn't matter. Well, the Spectre bug and the meltdown bug demonstrated that they can do timing attacks for something that is speculatively executing, which is at the high-end microprocessors, which they all do, and figure out what the values of those bits are. So that was a real shock to computer architects. So we have to do something about that. So that's pretty bad. Moore's law is over. Dennard scaling is over. There's nothing around the corner, and the security problems are terrible. So what do we do? So John Gardner, the person who gave us in the United States Medicare, kind of our version of universal health care for some people, said, what we have before us is some breathtaking opportunities disguised as soluble problems. The definition of an optimist. Okay. So let's talk about opportunities. Next phase of the talk. And the software-centric, what people are programming in, what we teach people to program in is these wonderful scripting languages, incredibly productive, but not so great for execution, and I'll quantify that. The hardware-centric thing, as far as people like me know, the only option left until quantum computing works is domain-specific architectures. It concentrates not on general-purpose computing, not lifting all boats, but just on some narrow area, and it does those well. Not that, hopefully not too narrow, but it's not general-purpose. And you could do both. And what are called domain-specific languages, or maybe libraries for productivity languages, have raised that level of abstraction that lets us innovate below that. So how slow are these scripting languages? So this is done by Liserson and Butler-Lampson at MIT in a paper that's going to appear, and they measured matrix multiply just to kind of scope how bad it is. So going from Python to C is a factor of 50, 50 times faster, right? So as John says, he used to be a compiler guy, and if in C or C++, some language like that, if you could make things go twice as fast, you'd be like a hero, right? So there's an opportunity for a factor of 50 improvement if you can make Python run as fast as C. So there's like Turing Awards on the floor waiting to be picked up. If you only got a factor of 25, only a factor of 25 faster. But that's just starting. Okay, let's put it on a multi-core computer. How much more can we get, speed up can get? Another factor of 7 there. How about we optimize it to the memory hierarchy of all the caches? We get another factor of 20, and then there are these 512-bit instructions, 512-bit data path instructions, and there's another factor of 9. Altogether, that's a factor of 63,000. Right? If you you might only get a factor of 1,000 going faster by going from Python. So what a tremendous opportunity to be able to do that. And maybe it can be, maybe it's not just compilers, but maybe you would have some architecture support to pull that. But there's an opportunity where there's orders of magnitude speed up for innovation in running important programs in Python. So I think I just said that the domain-specific architecture, it's the idea, the one thing I just want to keep in mind that it's called ASIC for application-specific integrated circuit, that kind of describes the tool flow. It's not really a chip that only does one thing. There's still software. Software is still a good idea, but it narrows it to a domain. It's not supposed to be good at everything. And why? Basically, because it's narrow domain, there's things that didn't work for general-purpose computers that can work. So for parallelism, single instruction, multiple data, when it works, is much more efficient than the MIMD one for classic general-purpose multiprocessors. Similarly, very long instruction words is much more efficient than the speculative out-of-order design that we do. The latter two are more popular for general purpose, but if you can get away with it, the other ones are more efficient. Memory bandwidth. Caches are one of the great ideas of computer science, but there's times when caches don't work. If you know the application well, you can do a better job than probabilistically loading things. And then you don't need all the precision necessary. You don't need IEEE floating point at 32 to 64-bit. You may even be able to get away with narrow integers. So that's why these domains can win. And like I said, the domain-specific languages gives you a software path. So what one area going to improve? Here's an area where the number of papers are growing by Moore's law. Right? Moore's law is still alive in the number of machine learning papers. So if going to archive and you look at the right areas, it's, it's probably more than 100 papers a day. If you want to stay on top of machine learning, you probably need to read 100 papers on archive a day. So a popular area. Google announced in 2016, I guess just 3 years ago, they said, by the way, we thought you'd like to know, we've built our own chips for machine learning. They're at least a factor of 10 better than the competition. That's all they said, right? So that got the attention of everybody. Intel went and bought a couple of companies in machine learning. There's probably 100 startups now that are doing hardware for machine learning, and Amazon has announced a chip that they did, and other people have done that. So here's an article about the first one they did. This is what's called for inference, the kind of the production part of it. If you use Google, you're using it. It's used for that. Its most famous use was to win the AlphaGo, the Go championship that was done in Korea, and there's an article about it in a recent Communications ACM if you're interested. So it's really different on the inside than general purpose microprocessors. The biggest difference is, let's see. The biggest difference is this multiply unit. So typically you might have, I don't know, 4 or 5 multiply units. This is 65,000 multiply accumulate units on that, 65,000 of them. Since they do a multiply and accumulate, the clock rate isn't that high at 700 megahertz, but 65,000 times 2 operations times 700, that's 92 tera operations per second. The other thing that's a distinguishing feature is the memory is rather than having really big caches and things like that dominate most chips, these are just dedicated use for the memory for neural networks. It's like 3 or 4 times as much as you'd find in GPUs. So it's really tailored to this application with a lot more compute units. How much better did it work? Well, comparing the GPU to the CPU, it's maybe in terms of performance per watt was a factor of 3, but we got factors of 80 over CPUs and 30 over GPUs. For production, this is not research machines. Production machines, you get factors of 2, that's a big deal. Now, the way we measured this was using production applications at Google, which was great because that was important for Google, but nobody else could duplicate this work because they can't have Google's apps. So a year ago, we started working on a ML perf, and you think of it, for those in computer architecture, it's like the spec benchmark suite for ML. There's 39 companies and 7 universities. They've had their first training deadlines. The second one will be, I think, this month, and they're going to do inference as well. So now we have a standard set of benchmarks for machine learning, and what's happened in the past, once you agree on benchmarks, that's accelerated progress in the field because everybody can agree what goes faster, what faster mean. What's the demand for training? This is by people at OpenAI in San Francisco. There's Moore's law, and if they look at the state of the art, how much training can they consume, it looks like that, right? So it's performance, instead of not doubling every month, it's doubling every 3.5 months or a factor of 10 every 5 years. So if you're a computer designer, you hate people who say computers are fast enough. I don't need faster computers. You don't like those people. You like people like this, right? I need every cycle you can give me. I want a factor of 10 every year. Give me everything you have. Google has announced the first generation was for inference. The second generation is for training, which OpenAI wants. So what was announced 2 years ago was this. This is 4 boards, and it's a little hard to tell from this diagram, but there's what are called heat sinks on it that are this tall, and all the air has to flow because it's so hot. And this puts 256 of them together, and this is 11 petaflops, would make it a top 25 supercomputer. Now, this is 16 and 32-bit floating point operations, because that's all you need for machine learning. The supercomputers are using 32 and 64-bit floating points. It's not quite the same flops. So that was announced 2 years ago. Last year they announced the 3rd generation, and you can see that this is now liquid cooled. They don't have the high heat sinks, but there's liquids flowing through things to cool them off, and they have a bigger system. So this is now more than 100 petaflops, which would make it a top 5 supercomputer. And Google puts these things into the cloud, so you can go rent supercomputers for machine learning to help you satisfy your training workloads. And not only does it have a lot of chips, it can actually speed up pretty well. Here's a paper for a standard machine learning benchmark. It is in MLPerf, and it's showing how you can get these kind of classic curves where the more chips you do, the more that it speeds up. Okay, so where are we in computer architecture debate? It's a really exciting time. Maybe it's like the early days of parallel computing. All these different bets are going on. Google is betting on TPUs. They have 1 or 2 cores per chip, really big multipliers on that. Instead of caches, it's software-controlled memory. Nvidia has lots of cores on the chip, lots of threads. To do this multi-threading, they have 20 megabytes of registers. The registers are bigger than their caches. They have smaller multipliers and what's gather, scatter, and hardware and coalescing hardware. That's their bet. Microsoft, so far, what they've revealed has been betting on FPGAs, that stick FPGAs in every server in the data center, and you can tailor it to a particular application. As I said, Intel, besides its standard cores, I'll wait for the music. Okay, wait for the music to stop. Okay, it's also got caches and stuff like that. But they also bought Altera, which was the big alternative provider of FPGAs, and they bought people who do things like the TPU, a bunch of startups, and at least 100 startups. So it's an exciting time. People would like to tell me, ask me. I'm a Turing Award winner. I should know the future. I don't know the future. The marketplace is going to settle this. We'll know. We'll look back. 10 years from now, 5 years, we'll look back. Of course, it was that one that was going to win. But I can't tell which one's going to win. And it's a very exciting, interesting time. Kind of a cornucopia of architectures right now. Okay. So one opportunity is domain-specific architectures. I was always jealous of people like Margot because she was in the places where there was open source in what she did. There's open source databases and open source operating systems. So why those but not instruction sets? So first of all, who cares about instruction sets? Well, it's like, why can't Intel x86 sell mobile chips? They're almost all the ARM, which is a RISC architecture. ARM can't sell servers, they're 99%, and then IBM is still selling these mainframes with this 60-year-old architecture, and it's because of the instruction set. It's the most important interface to the computer. It's where the software meets the hardware. So instruction sets really matter, but yet we still don't have an open one. Now, there's a downside for proprietary instruction sets because if it's tied to a company, what happens when the company runs into trouble? The instruction sets get into trouble. So DEC, this company in Boston, went out of business and it took 3 instruction sets down with it. Intel so far has abandoned 4 instruction sets that it tried. So if you had your software in that, you would have been switched. MIPS was first sold to another company and then it's by one of these AI startups. And then Spark, which I was involved with, was acquired by Oracle, but they closed it down. And ARM was bought by another company. It's certainly in business, but people sometimes worry about who owns ARM. So that's a downside to proprietary instruction sets. With that, where did RISC-V come from? It's called RISC-V because it's the 5th RISC architecture that was Berkeley. I did the first 4, but Krista Sanovich and others thought they would reflect Berkeley roots by calling it RISC-V. We were going to do a project, about 2010. What instruction set? Well, x86 and ARM made sense, but A, they were really complicated instruction sets, and B, they were restricted. We weren't allowed to use them. Intel was funding us, but they didn't want us to use that instruction set architecture. So Krista and others decided to do a 3-month project to do their own clean slate instruction set. 2 graduate students, Andrew Waterman and Jensip Lee, and I provided wisdom to the project. It took them 4 years, but they built a lot of chips as well as define the architecture. And then we had this weird thing is that if you're in academia, companies complain about what you do all the time. But they started complaining about why are you changing your instruction set from fall to spring in your class? And why do you care what we do with our instruction set? And we found out there was this thirst for an open architecture. They looked around at lots of them, and they found ours and liked it. So we thought that would be a really cool thing to do once we understood it existed. So we did it for our own use, but the people came to us and wanted an open architecture. So what's different? It's free. Anyone can use it, and I think what that means is anyone can use it There'll be more competition, which will be more innovation. Right now, there's probably more organizations building RISC. Surely there's more organizations building RISC-V than any other instruction set architecture. It's for both the cloud and the edge. There's a 32 and 64-bit version. A big thing that people are worried about right now is security and trustworthiness. Some countries are worried about getting cores from other countries because they're worried what's in it. So if you have it yourself, you can design it yourself, you know what's inside. And also, as I'll explain, the RISC being open allows for open source cores, so you can get ones and download them and see what's there, and there's no secrets. It's a simple modular instruction set. First of all, 25 years later, you can learn from the mistakes of others, so you don't have to make them. It's much simpler than the other ones. The manuals are, I don't know, a tenth the size or something like that. Because of this domain-specific architecture, you need to be able to add custom instructions, and there's space to do that. And then, because universities can lose enthusiasm for a project, people worry about betting on universities, we looked at what the Open Source Software people did, and they created a foundation. So we created a foundation for RISC-V, which owns it. The foundation, this is the foundation growth going up and to the right. Total, there's almost more than 240 members of it. This is some of the members. The ones I'll mention are Nvidia announced that every Nvidia GPU chip will have a RISC-V controller in it. Western Digital announced that for every disk drive, they want to bring computing to the disk drive, and so every disk will have, and that's probably a billion cores per year or something like that. And there's many others. We expect to see more announcements a lot over the next couple of years. Lots of parts of the world are working on RISC-V. We just have a new CEO, Callista, who's joined us. Expect good things. We brought out, it's in all the textbooks I'm associated with, and we even did one online, a thin one online, and we made those available for free in many languages to help people do that. And we're not the only ones. Nvidia announced an open architecture for, like the TPU, a domain-specific architecture, and they make the software free, the instruction set architecture is open, and the implementation is free. So that's another example of open architectures. This is an idea that's catching on. Okay, and then there's some confusion about the open source architecture versus open source implementation, so let me just go through that. So there's specs, like an instruction set architecture, or POSIX, like for operating systems, and there's designs, like RISC-V, Rocket, or Linux and software, and there's products around that. Okay, so there's three types of these things, three types of designs or specs. There's free and open. That means anyone can use it. You can design it yourself, get it from others. There's licensable, like company owns it and you pay to use it, and there's basically closed. Somebody owns it, and you'll get in trouble if you use it, okay? So three of each, 3 by 3 should be a matrix. So how does that work out? So if we do a closed spec, the only thing you can do is closed designs, right? If a licensable spec, then you can either do a closed design yourself and licensable design. So ARM typically, I've been told, charges about $5 million plus 4% if you license one of their designs, and if you want the right to do it yourself, it's about $25 million. RISC-V is free and open, so you can do all of these things. So what's open source? Open source is that green box. So you need an open architecture to have open designs. You can't have open source designs without the open architecture. Okay, what can happen with this? So this is a former student of mine. He was able to do this in 7 months, and it's a full RISC-V core. It's got, I think it was 8 cores, 8 regular RISC-V cores and 12 of these AI accelerators, and he put this together on a board, and he sells it for $3. Remarkable, kind of a remarkable thing, but they do that and stuff like this in China. I think another real opportunity with open architecture is around security. So for people who've been in this a long time, it's embarrassing how bad security is. It's hard to explain why it's so bad, but that's where we are today. So security people like things that are open. They don't believe security through obscurity is not a popular idea. They want everything to be open. So they like RISC-V. But I think another argument is since it's open, everybody can work on it. And security is really hard. We need all the best minds. We want not just people at a couple of companies. We want everybody, including people in academia, to work on it. And then I think there's a great opportunity, particularly with RISC-V, because there's a full software stack and a full architecture implementation. And FPGAs work well enough. You can fit everything into one FPGA, and you can run it maybe 100 megahertz, but that's still fast enough to run real software on it. So we could go from security people being critics, poking fun at Intel or ARM for mistakes they made, to putting something out there that they can see if it works. You could subject to attacks. You could offer rewards. And so because it's an FPGA, we could iterate and make progress at once a month. For security, to be realistic, you have to has an intelligent opponent, right? You need to put something out there that the intelligent opponent can attack and see how well your ideas do. Right now, we haven't done that so far, and I think this is going to be hopefully a great opportunity to make security, progress in security we desperately need. And I think it's already can become the kind of the most attractive instruction set for security people. Okay, the last part. Software advances can inspire innovations. One of the revolutions in software engineering was the Agile Development. This was a manifesto that was done in 2001 that said instead of these heavy documentation specifications, let's just do quick but incomplete prototypes by small teams, and then we'll show it to the customer, get feedback, and that's a better way to do it. Iterate with small teams. And they do these sprints typically to get the incomplete prototype, and they would last about a month. And so can we do that for hardware? The CAD software will do it, but how can we do hardware with 4-week cycles? So if you think about it in this kind of expanding iteration, if you can do it in the simulator, that's just software, right? If you can evaluate the idea in software, there's no reason that has to take more than 4 weeks. Field programmable getaways are a little harder, but you can do billions of instructions or tens of billions of instructions, so you can run a lot more software. That's pretty easy to do. And by the way, you don't even have to buy FPGAs today. They are available in the cloud. You can rent them in the cloud. So you have kind of no excuse not to evaluate the ideas of FPGAs. You don't have to buy anything. And then to get a chip, you have to put it through this ASIC CAD flow. If you want to get an idea, not to see how much area it takes or how much power, you can kind of get what's called the layout of the area. That's a necessary step for the chip. Now you could stop there. You'd have a pretty good estimate of how much it would cost and how much power it used from that. But that's like, running a marathon and stopping, 200 yards before the marathon, because I could accurately guess how long it would take to finish, right? The one thing we can do in hardware that software people can't, they're stuck in cyberspace. They show their mom, oh, yeah, there's bits up there. But we can build physical things. We can give our moms pins with our chips on it. There's the excitement of when this chip comes back, is it going to work? How much power is it? How fast is it going to go? So there's this kind of crescendo effect of building hardware, provided you get the chip back. Well, that seems like that would be really expensive. It's not. There's always been the ability to do test chips to see if the thing is going to work, very small test chips. But where we are with Moore's Law, small test chips have millions of transistors in them. So you could put one of the RISC-V cores in the Nvidia accelerator in that chip. So anybody can afford to build real chips today. This is standard from TSMC. If you want to build a really big chip, it's much more expensive, but small chips are within everybody's wheelhouse. Okay, so Berkeley built, and as a result, students at Berkeley have built lots of small chips. So students come out having built 5 chips. So they have really self-confidence that they know how to build chips because they built a lot of ones. So wrapping up, and before I do questions, so 50 years of computer architecture, the lessons. Software advances can inspire architectural innovations. We saw that in microprogramming and the RISC stuff. These days, it's too early to say, but there's excitement about the open architecture and agile hardware development. Raising that interface led to opportunities like assembly language, a high-level language led RISC. Now, these domain-specific languages and libraries are letting us do domain-specific architectures. And that the marketplace settles these debates. The 432 lost out, but winners can last decades. This proprietary versus open instruction sets and DSAs versus general purpose ones, it's too soon to tell, but it's, we'll see, we'll let the marketplace settle it out. But as John and I say, and as as we wrote, that we think this is an exciting time. It's going to be another golden age for computer architecture. Thank you. Okay, questions. To get questions, I need a first question. Margot didn't tell you I was a wrestler. I'm not letting you out of here. Okay, yes.
What's your best lift?
My best lift. Good. I can do this. I can do this in pounds and kilograms. I went to China and I had to figure this out. So when I was on my 50th birthday, I bench pressed through. And for people who don't know weights, there's all kinds of things you can do. Conventional wisdom is bench press is the thing. That's the thing you talk about. I bench pressed 325 pounds, which is almost 150 kilograms. So I don't usually, that's not usually a question I get, but yes.
So aside from the ML applications, do you see another domain that's sort of begging for architecture?
Oh yeah, I mean there's lots of them. I think video encoding and decoding. Those are standards that evolve over time, and people want it to go better. I think you could argue that GPUs, graphics, is one of those. That's kind of graphics. That's generating graphics. There's my colleague Jonathan Regan-Kelly did Halide, which is a system for analyzing images. So I think there's this. I guess the startup company here, D-Wave, is doing regression. Is that right? But I think there's areas where there's a real market and a real need, and if we want those to go faster, as far as we know, you have to do accelerators. Machine learning just was like fell in our lap, right? Machine learning just took off, and it happens to be pretty right now. The models that we know are kind of understandable. Of all things, they want matrix multiply. If you asked a computer designer, what do you want me to make go faster, and he or she had a wish list, he'd say matrix multiply. I know that one. I know. If you said pointer chasing, I don't know what to do. Matrix multiply, we know how to do. So that fell in our lap, and machine learning looks like it's good for translation, speech recognition, image analysis, and it's working in a bunch of other areas. So it's kind of surprisingly narrow. It's got the software stack that's in these higher level systems, and it's very important and applicable. So that's the one that was sheer luck, right? That came along. The bad news for machine learning people is Moore's law ended just at the wrong time, because they have this huge opportunity. The first word in machine learning is machines, right? They want faster machines so they can explore this space, because we don't know how far it's going to go. So I'm pretty sure it's not limited to that. Like I said, I think if you were to go to the Computer Architecture Conference and ask anybody there, they say, as far as we know, the only path left is these architectures. And in fact, the paper that I referenced, there's room at the top by Leiserson et al., they're saying the future looks very bumpy, right? They're saying the past with Moore's law, it raised all boats and everything went faster. What we're going to see going forward is these narrow areas where you see these giant speed-ups and other areas where nothing will happen. So we're going to have kind of a lumpy road going forward where people will figure out things, how to get these big step increases, but other areas won't. And this is something I'm trying to convey to my colleagues at Berkeley is, Moore's law is over. And about 15 years ago, I said, the future is multi-core. And they said, I don't know if you're right? And I said, the future, Moore's law is really over, and the people would argue about that. But I'm confident that these things are happening. They're going to be big changes to our ecosystems, right? And we're going to have to react to them. So if you're a researcher or a student or an engineer, this is exciting times. People need change. They need new ideas. If you're a business person, these are scary times, right? If you're the CEO of Intel, what the hell are you going to do, right? This is tough for financial prospects, but exciting for people who like to develop new ideas. Yeah.
If I go to implement my own processor and hardware, are hardware patents going to be an obstacle? Like I just copied somebody's implementation from 1960.
Great topic. I think there's something called, the question is, if I build something myself, am I going to run into patents? And so I think that did happen with open source software, is that there were companies that would sue people for software patents. So I think this is, there's something I'm trying to work on that if it works, I'll announce it and let you know about it. But I think that the goal, when I got to Berkeley as an assistant professor, they said, Dave, we don't care about the number of papers you publish, the number of citations, we care about impact, right? So I think the real impact opportunity for open source hardware is to not ignore patents. So the specific example you said, suppose I copied something from 1960. You'd be golden, right? Because patents last about 17 years. So I think what the real challenge is to build open IP that anybody can use and be patent aware. And so one idea would be exactly to use expired patents. If this patent was expired, was granted in 2000 and you re-implement that idea and that patent is expired, I don't understand how you'd be sued. But I haven't run that past IP experts. Part of doing this would be to reach out to our lawyers and how do we solve this problem? How do we build IP that's not going to leave us open to patent trolls? And I think we can do it, but we just have to be a little smarter about it. And if we do that, I think we could have giant impact.
Do you foresee this stuff, you mentioned before, say, capabilities in hardware. Do you foresee this stuff bringing
What?
Capabilities?
Capabilities.
Do you foresee this stuff bringing ideas like that back into it?
Yeah, the question was about capabilities. So there's a research group in Cambridge who was excited about capabilities. They're modifying RISC-V to do that. So I think what's exciting about this is you get a whole software stack and a working implementation that you can put in an FPGA. That's your starting point. So then if you want to try ideas out, you can go modify that. So you don't have to start with a clean slate of paper and build all that. So that's, and that's why many researchers are using it. Besides the commercial consequences, it's a perfect thing for researchers because you can actually build something that can work and you can see how well it works. And there's low risk, and I think there's a couple of, at least 2 or 3 other people who are looking at capabilities in the architecture. RISC, just to demonstrate its portability, there's a 32-bit version, 64-bit version. Kind of as a joke, they also made a 128-bit version just to show that they could. And there's some people who are excited about having that much address space for security reasons. So yeah, it's a great vehicle for those kinds of things. I think we could go into kind of we could be synthesizing systems of the future to see how well they work with this current situation, which is one of the reasons we called it the golden age. Yeah.
Dave, one of the things that has driven a lot of the development of computers is the communications that ties them together, and really led by fiber optics. Do you see that being a limiting factor, the bandwidths available?
The question has to do with communication speeds. I don't personally see that as an obstacle. Now that I'm working in Google, I can't tell you what they've deployed. I'm writing papers and hoping the reviewers will accept them so I can tell you. But they're pretty damn fast. The network that's connecting these computers together. My colleagues at Berkeley have done a paper that was in Nature where they showed how you could put optical directly on silicon, right, so that they could actually do that. So I think the packaging is the challenge for that, but technically you can connect optical to CMOS and have it work. So I guess I don't see that one as the limit right now. Bigger challenges have to do around the memory capacity, memory speed. I think for machine learning stuff, that's where that's got more focus. Yeah.
Yeah, so with a lot of DLLs being, a plethora of DLLs available in the market, right? Every startup is coming with their own accelerator. Do you see what's happening to the life of a software programmer? Are you going to reenact the 1960s or 70s where everybody have a different ISA and you don't know how to program one hardware versus the other? Is there anything to
Yeah, so the question was asking about, with all these startup companies doing DSAs, what's going to be the impact for software? So I think, well, most of those startup companies aren't going to make it, right? On average, 90% of the startup companies don't make it, right? So if you go to a startup company, try to get a good salary because, don't sacrifice your salary for your incredibly valuable stock because, that may not work. Independent of the startup companies, Hennessy and I think hardware is going to be more heterogeneous, and we're going to have to figure out how to incorporate software that way. Now, I think the positive things about machine learning is if you think of an application having, all kinds of stuff and about of computing, the amount of lines of code for like TensorFlow or PyTorch is not many lines of code, like thousands. It's not millions of lines of code. So that part I can imagine being moved to the accelerators without, hero work on the part of software. If that's true about these other applications that I talked about, like image analysis, image analysis or encoding, decoding. If it's a small compute-intensive kernel, you're kind of replacing a library, I can kind of see how that works. But I don't know how what's all going to happen. In terms of the instruction set architectures for the DSAs, if it's a split between a standard instruction set and then the machine learning piece, RISC-V is very popular there. So I wouldn't be surprised if we'll see that kind of split. Well, the one that's like that is wave computing. They pick MIPS, so it's a simple RISC architecture with an accelerator. Okay, I think this pause, so now you get to hear my life story. And the most valuable slide that you're saying. Okay, so, and the reason I tell this story is some people, particularly graduate students, assume if you've had some success that your road was just skyrocketed right to the top without a single distraction all the way there. And so I need to let you know that's not the case. So I was the first from my family to graduate from college. Oh, I can do that with the controller. So that was my goal. I was a wrestler in high school and college, and I had absolutely no plans to go to grad school. The success was getting a bachelor's degree. And then what happened was I was a math major because I did that in high school, and at that time there was no undergraduate computer science degree. That came a little bit later. But I took a course from a new faculty member at UCLA, and at the end of the course, in my senior year, I casually said I was working at my dad's company in downtown Los Angeles, and I'd sure rather do computer stuff to make a living rather than support myself working in a factory. So all on his own, he went and got me a job. He talked to the faculty, got me a job as an undergraduate. And then I was married at the time, so I talked to my wife. I said, wow, this is fun. Maybe I could go to get a master's degree. And so she said, well, that sounds good. And then I got put in an office, and everybody in the office was getting a PhD. So I went back to her and said, what do you think about PhD? He says, well, if you think you can do it, why not? So that's how I went to graduate school. Now, we got married and had kids young, and then we were living on a 20-hour-a-week RA ship, and then the grant ended. So that was pretty bad. So I got a job at a nearby company that built airborne computers. And it took me 3 more years to graduate because I had 2 kids and was working and stuff like that, and 7.5 years to PhD. So the great thing about being around 40 years ago, 7.5 years to a PhD is not bad today. That's not so bad. It was really bad 40 years ago. My in-laws at the time, who were certainly my biggest fans, referred to somebody who took a long time to getting a degree as pulling a Dave. That was okay, and then accidental precursor. So my wife grew up near Berkeley. Both of her parents went to Berkeley High School, and she loved Northern California. She was forced to move to Southern California when she was 11 years old. So while I was in the interview process, she kept asking me, what about Berkeley? What about Berkeley? I told her I'm at UCLA. UCLA's lower in the pecking order. Not much chance that's going to happen. So she finally forced me to call the chair of the department at Berkeley to find out my application. And so I called him on the phone. I still remember the guy's kind of a famous mumbler, so I had to concentrate. It's hard. Hi, I'm Dave Patterson. I've got some offers, but I hadn't heard of Berkeley. It's the one place that I haven't heard from. If you're interested, I'd be willing. And so, do you remember my application? And he says, well, Dave, you're in the top 10, but not the top 5. And I had this complete, thank you, Ellen. I hung up in complete relief because that wasn't as embarrassing I thought. I found out later he said that to anybody who called. but I was relieved. But he took my application out, and then he gave it to a guy who happened to be visiting Southern California, and he stopped by my desk at UCLA, and we had a good conversation, and I got invited to apply, and I got a job offer. And then the first project I actually did with that guy was way too ambitious. We were going to do our own operating system and our own chips and all compilers and all that stuff, and we had no resources, no grants or anything like that. Fortunately, I took a leave of absence to Boston at DEC, and it gave me 3 months to rethink my career, and I came back and did the RISC stuff. Otherwise, I surely wouldn't have got tenure if I hadn't taken that leave. And then tenure wasn't easy. Computer science favors conferences. Almost all of their fields, the conference papers come from nothing. That what they count as journal papers, and the RISC stuff was too recent, but I was able to squeeze through there. Okay, and after that, things got better, although my papers still get rejected by the jerks on the program committee. Okay, so so 40 years as a professor, what worked well for me? Maximizing personal happiness versus personal wealth, kind of you growing up in Northern California, I think. Not Northern California, you grow up in North America, you kind of think to be happy you have to be wealthy. That's kind of the things. And so that's not true. There are very wealthy, unhappy people, like our president, my president. He's not real happy. So I made decisions that made me happy, so directly and necessarily for wealth. Family first. If you especially if it's assistant professor or anybody who gets into a new career, there's all these people asking you to do things. And if you don't make your family first, your family can be fifth. So when opportunities happen, I have two sons, and so there was something called Indian Guides, and we did Indian Guides together, and I was the Cub Scout den mother, I think, and I was the assistant soccer coach, and their field trips I was always there. And so when your incredibly cute, charming young sons grow up to be hokey, moody teenagers, and Dad, you were never there. Let's go over the list. Indian Guides, soccer coach. All right, well maybe you were around after all. And in fact, speaking of family first, I'm helping my grandkids with their algebra right now. Passion and courage. I like to think I'm an intellectual guy, but really I'm, as you probably can guess, I'm pretty passionate. And ironically, the physical courage that comes from wrestling turned into intellectual courage. I feel like when there's some debate that it's my personal job to stand up if it's not right intellectually. And so this works into we swing for the fences. They told me they value impact, so we don't bunt for singles, we swing for the fences. The project has to be capable of having high impact for me to do it. Now, in terms of the courage and standing up, one of the things I had to stand up about was when DARPA cut funding to academia under the second George Bush administration, Ed Lasowska and I tried to complain about this, publicly about it, and we couldn't get people to join us. Because they were afraid of the guy who's making these decisions for good reasons. He would probably cut people off, but we felt it was our job to complain about it. Now, the good thing about that is that if you, what's the bad things about it? The bad things about it is one of my colleagues quoted this next saying, friends may come and go, but enemies accumulate. So, if you think about it, even for undergraduates, you remember the people you hung out in junior high and they kind of fade away? Enemies never forget. So as far as I know, I made two enemies in my career. One person who we didn't appoint who wanted to get appointed to a position there, and I am happy with that decision. And this guy at DARPA. But now the guy at DARPA, if you make, the enemy of the enemy is my friends, and he was a pretty unpopular guy, so... But nevertheless, the thing to take away is, pick your enemies carefully because they're going to be around for your whole life. I kind of believe just in my DNA that you can win as a team versus an individual. Surprisingly, the wrestling teams I were on in high school and college, those coaches believed that if we bonded as a team, we would be more successful, even though wrestling is an individual sport. And I just believe in my DNA that a team can be formed together and can win. And quoting Fred Brooks, there's no losers on a winning team and no winners on a losing team, right? As long as you're on a winning team, no matter what you're doing, you win. And if the team doesn't win, you can't win. I think I'm good at seeking honest feedback and learning about it. If somebody doesn't like your ideas, send them your paper. They'll tell you what you think, and you can learn from that. I think there's a flip side of this that's another lessons learned that you can take away, is the guaranteed danger sign is that I'm the smart, if you meet somebody, the smartest person in the room. So in my career, there's about 6 of these. The person who I didn't want to support for a position at Berkeley, he thinks he's the smartest person in the room, and he's kind of in my field, and everybody hates that guy. The founders of Enron thought they were the smartest people in the room, and the founder and the CEO are both convicted felons, okay? The president of an Ivy League university, whose name I will not reveal, who thought he was the smartest person in the room, dug a giant hole in nearby and was fired from his job because he was going to spend billions of dollars to fill that hole with buildings. And I even have an the brother of my ex-brother-in-law thought he was the smartest person in the room, and he's a convicted felon, okay? So why is this? They probably are all smart. I think what it is, if you think you're the smartest person in the room, you think you can't get any useful feedback from anybody else because you're smarter than all of them, right? So you just do things without getting feedback on it, and that's a recipe disaster. So besides that, anyways, if you hear somebody who thinks they're the smartest person in the room, run away. Okay. One big thing at a time. I still can remember kind of waking up on a sunny morning, and it was like God spoke to me. It's not how many projects you start, it's how many you finish. It was actually, that phrase rang in my ears. It's kind of an obvious statement. But once I heard that, I was more careful when I volunteered to do things. I didn't do only one thing a year, but I would do one big thing a year and small things. So when Hennessy and I wrote our textbook, that was the one big thing we did that year. When I was president of ACM, that was the one big thing per year. So, and it turns out that at least by academic standards, if you only do one big thing per year, but you do that for like 30 years, you can get a lot of things done. But I would consider that one. And finally, I'm a natural-born optimist. I think, especially in research, there's times you're not sure if you're going to make it or not. And I think it's better to err on the side of optimism. So my story to illustrate my optimism goes back to high school. And I'm 16 years old, and I'm dating a girl who I really like, and I was asking her if she would be exclusive, that we'd only date each other. At the time, we called that going steady. So I screwed up my courage, asked her to go steady. She had gone on lots of dates. She was only 16, wasn't sure that going steady was a great idea. So she said, well, Dave, you're such a nice guy, I don't know how to say no. So to me, as an optimist and a logical person, not a no was yes. I said, great, and I hugged her. So in her mind, while I was hugging her, she said, well, I'll let him down gently later, but we've been married for 51 years now. All right, and here's my last slide. So if you've been married, well, at 50 years, it's a big deal. You can get a letter from the president if you want a letter from that president. But it's a big celebration. So people, when you've been married that long, they want to know your secret. So even for people who are, marriage age, it's going to be valuable advice. And even if you're not, file this away. So it's 9 magic words. I'll even give you some hints. 4 of the words are I and you. So the first, and you have to say all of these words, right? I was wrong. You were right. I love you. You can't say I was wrong, you were right, you're a jerk. Okay? And so if you want a long relationship, remember these 9 magic words. And with that, I think I'm all done. Well, I could do more questions, but I don't know.
I think there's like another, the reception, and I thought...
Am I too early?
No, I thought I was supposed to say something.
At the reception.
Oh, it's at the reception. Okay. So reception in X860, and we're just still getting set up.
So I could do questions. All right. All right. I can questions for any part of my life or advice. Yes.
Good a question this is. You were saying security through obscurity isn't very popular just in the industry in general. Do you want to speak about that as to why that is?
It turns out, the security goes back hundreds of years up to when people were doing for spycraft and stuff like that. And this is this lesson of which is, I think, common. You'll hear this if you take a security class. goes back hundreds of years. The idea that I know what we'll do, we'll invent a mechanism and we'll keep that mechanism a secret and we'll encode a lot of important information in that secret mechanism. That didn't work because eventually the secret mechanism would get revealed and then all the secrets would come out. So in World War II, the Germans had the Enigma machine with the secret mechanism, right? And then once the British broke that, it helped them lose the war. So they believe the mechanism needs to be published so you can see if there's any flaws in the mechanism, and then you can keep a small piece secret, but not try and do that. So that's the philosophy of security or encryption, and that's gone back for hundreds of years, and that's how that community thinks. So they like the idea of open software, and and one of the things we found out with the WikiLeaks was there was attempts by governments to insert things into the technology, and so that made people worried about what's in the hardware that they have. So having open architecture and open implementations goes along with the goal of trying to have more secure, trustworthy systems. Yeah?
Are there any promising alternatives to transistor-based sequential computers that you should think about in the coming decade?
The question is alternative transistor-based sequential computers. So I don't know if computers are sequential anymore, single-threaded machines. Well, microprocessors have lots of threads, right? There's no problem building lots of threads. But transistors are incredibly attractive switches. They can be manufactured in the hundreds of millions at very reliable low costs. So it's a difficult technology to overtake. There's people who have excitement about carbon nanotubes and things, but apparently those are also like 10-ish years out before something is commercially viable. So as far as I know, there's nothing right around the corner, because it's got to be fast and cheap and reliable and scalable and all those things. So transistors are pretty amazing. So even as they're slowing down, they're not trivial to replace. Yeah?
A little about some Moore's law slowing down, but then sort of certain fields like machine learning, you can kind of take advantage of the domain-specific pieces. How much of those sort of taking advantage, is that like low-hanging fruit that you can take advantage and then you sort of back to Moore's law?
Yeah, that's a good question. The question was, what's going to, you could get, how sustainable is this domain-specific architecture given the ending of Moore's law? And so as an optimist, as I already did myself, I'd like to believe that we'll keep coming up with ideas. But David Wetzlaff at Princeton did a paper where he looked at a lot of examples of accelerators in other fields, and he felt it was a one-time step, and after that you're back to whatever the underlying technology is. So I'm kind of an optimist. People will invent new ideas, particularly in something that's moving as quickly as machine learning, and be able to do that. The good news about machine learning is it's highly, especially the training piece, it's very parallel. So we can keep building bigger and bigger computers, with even if the accelerators don't get a lot more efficient. The other thing, of course, that Google has done is, since we're building for the data center, not building for desktop, we can do more aggressive cooling things. So we can keep I said one of the slides is Dennard Scaling was we can't raise the temperature anymore at room temperature. In a data center setting, you can keep doing that. So there's some reasons to expect Google to keep building and other people to keep building big training machines that will keep at a rapid pace, even if the individual chips won't be improving as fast. Yeah?
Just in an era with more parameterized architectures that you build from known functional blocks, can you describe where are the key pain points where, as a computer architect, you need to do that intervention, as opposed to if you have a completely parameterized architecture, you can treat it as compilation all the way down?
Yeah, so it's questions about ease of customization. So the Chris Hasanovich and Jensip Lee and Andrew Waterman did a startup company called Sci5, and their vision is to have like a web page check mark that you click the boxes and you get a chip back with the boxes you clicked that's just custom for your design. So I think they're hoping to do that within a year or two. Now, as I was talking to other people today, if you're doing it yourself, one of the obstacles is just the cost of CAD software. ECAD software is millions of dollars. They're designed to be used by Intels of the world, so they charge a lot. So by doing it via a company like Sci-Fi, they've already paid for the licenses for that. There's this question about open IP. You know, can you populate this kind of web page with lots of blocks, right? And that's kind of a nascent industry. And you have to make the software piece work. You have to have how you're going to get software to this. And those are some of the obstacles. But there's reasons to be kind of optimistic in a lot of these areas, right? The domain-specific languages, you know, people trying to do open IP, you know. So I think that's, you know, again, part of this argument about this next decade could be the golden age. If we can address some of these problems, which seem not like rocket science, seem plausible, then it could be a pretty exciting future. Yes?
So, just finishing my undergrad right now. I really appreciate the story because I'm 34.
Okay. You can use the 9 magic words at 34.
I said that to my wife just now. And you highlighted compilation as a big opportunity.
That's one of them.
There's sort of this classic story of hardware and software people talking past each other. And so I'm sitting here being like, looking forward, how do I not do that in the future, right? Well, how do I make sure that I am getting along for and becoming a compiler guy?
The question is, how do we avoid hardware and software not talking past each other? Kind of, in this era, we need kind of the Renaissance person, right? To make progress in the domain-specific era, you need to know the domain, kind of architectures, and domain kind of software compiler technology, architecture, and implementation. So that's, if you can be this Renaissance person, there's great opportunities there. Kind of old-fashioned computer architecture, people would have no idea about the applications, right? That wouldn't be something they'd worry about. It's some C program. I'm going to make that go faster, and maybe not worry much about the compilers. If we go back to the early RISC days, it really was compiler people and hardware people, architecture people working closely together on this. The domain-specific architecture will involve learning about the applications as well. So that's where the opportunities are going to be. So there's going to be great opportunities there, but it's going to be a little harder to do that. You might want to go to graduate school, for example. Or if graduate school, I mean, compared to when I graduated, 40 years ago, a lot of people get PhDs today. To be able to do some of this work, you wouldn't think you have to have a PhD, but a lot of people who do that work do have PhDs. And the argument is you can get exposed to a lot of, people will teach you all these really important ideas that can be important for your career. For another 5 years, it may not be a bad investment to get that access to that technology. But at least a master's degree could help.
2 more questions.
Okay. Now we're ready. Okay, go ahead.
Since a lot of the optimizations we're currently doing with chips has to do with a little bit of the memory bandwidth, like the memory throughput. Do you see any major breakthrough coming in that area?
Yeah, the question is about memory bandwidth is an opportunity. That's a great point. I don't see any breakthroughs. I mean, there's already this idea of what's called high bandwidth memory, where there's something that's called a kind of a chip interposer, where you put the logic chip in small stacks of DRAM with really wide buses, 1,000-bit buses, so 4 stacks, each with a 1,000-bit bus. So that's really high bandwidth, but it has a limited number of chips. That's kind of the state of the art. That'll get slowly faster, but not some big breakthrough. But another thing I didn't quite say is that what's happening right now in this domain-specific architectures is all kinds of ideas that were rejected for general-purpose computing are being resurfaced in this new era of domain-specific. So ideas like asynchronous logic design, chips that have no clocks, analog computing, right, come back. And there's another old idea that could come back that's called processor in memory. That is, the processor is in the memory chip itself. You put processors in the memory chip itself. So people are investigating all these ideas in this new domain, and maybe one of these is going to work. And certainly if you put a processor in every memory chip, that would be and because inside the memory chips is actually a lot of memory bandwidth, narrow it down to get it off the pins, but inside the chip is a lot of bandwidth. There'd be tremendous memory bandwidth in there if that's the way to go. And that could be the way to go. All these ideas are being looked at. Last one. Okay, go ahead.
Your statement about future is multi-core. So, I mean,
the future isn't multi-core.
Yeah, 15 years ago you said it, but it was not true. Is it the memory cache coherence or something else has changed?
No, all the everything you buy is multi-core. I mean, you can't buy a cell phone that's not multi-core. So multi-core has happened. It's not something that's about to happen. It's history. Okay, I'll do one more question. Yes.
So Google does most of its machine learning in the cloud, whereas for privacy reasons, Apple's saying, well, it should be done on the edge, right? And you talked about the implications of architectures for the cloud. What are the implications for the architectures on our phone?
The same thing. It's the same challenge. I mean, the phone is equally challenged in terms of, certainly for power and speed up. So Google has announced something they call Edge TPU, and there are many startup companies building machine learning accelerators for mobile devices. The conventional wisdom is that you would train in the cloud and you would do inference on the edge. That's pretty, but there are people who are investigating to see if it's possible to do training on the millions or billions of edge devices as well. That's one of the areas. Okay.
Let's thank Dave.
Okay.